Okay, this is lesson 6 of the electricity module, and in this lesson we're going to learn about the IV characteristics of components. So that's the title, copy it down, and let's get started. We learned in previous lessons that we can make a simple circuit. So here I'm going to make a circuit. I'm going to have a cell. I'm going to plug in an ammeter, make that go circular, plug that in, and I could plug that into something. So say I plug it into a resistor. There it is, and I complete the circuit. Well, if I could change the voltage, change V, I could measure the current. That's where the words IV come from. Change the voltage, V, measure the current, I. And what that will give us is a graph that is like a thumbprint for this resistor. Now, to measure the voltage, I'm going to need to add a voltmeter. And if you remember, he's like Mr. Tickle. He goes around the thing you want to measure. So there's my voltmeter now. I'll colour him in a bit of red. And there's my ammeter, and I'm going to colour it in blue. Okay, now we've got one last problem. If you look at a battery, take a battery, there it is, boop. Usually those little ones are 1.5 volts. How am I going to change the voltage of that? Now in our lessons it's not a problem. All we do is we plug in not a voltmeter, we plug in a power pack. There's a symbol for a power pack. But if we couldn't, if we were stuck with a cell, then we could add one extra component. And this is what you'll see in your revision guide. And it's a resistor that can change the voltage because it's a variable resistor. So I'm just going to add that in, even though in real life we don't use them. So copy this in, variable resistor. And let's just annotate that, to change the voltage. Okay, I'm going to put that in green. That's just a little add-on that we need to be able to change it if it was a cell. So in textbooks you'll get it like this, but in real life we already use a power pack where we can change it ourselves. So let's have a look. What would we get? Well, if we put in a graph, and I've just downloaded this new pack, so let's give it a go. I'm going to insert a graph looking like this, and I'll explain why it's not the normal type. Here I'm going to label it plus voltage, and here I'm going to label plus current. Now you remember the symbol for current is I. I'm going to put a little bit of colour on it just to link them. There's my voltage and there's my current. Now if I had it like this and I did my experiment, what I would find is I would get, and let's use a nice colour, we'll use blue and we'll make it thick. There we go. What we'd get is we get a graph that looks like that. Now, why is it that we have this other way, this opposite bit? Well, if I hop back to it here, I can have here minus current and minus voltage. But what do those mean? Well, what that means is if I took my cell, there's my plus, there's my minus, if I swapped them around, so I might be able to do this, let's give it a go. Grab that, go there, grab that. If I swap them around like that, then the numbers now on my ammeter and my voltmeter will be minus numbers. So here and here, I'll get minuses. And the cool thing about that is you get exactly the same answer, but this time it just goes through to the minus. So that's our first graph. That's our first IV graph for a fixed resistor. We sometimes call them ohmic conductors, like so. So that's our first one. So let me summarize. We have measured the IV characteristic of a component. We've built a test circuit. I forgot to put that in. This is a test circuit. we have put the ammeter in series, we've put the voltmeter in parallel with our component, which in this case was a fixed resistor. When we graph it, we get a straight line, and if we change the polarity by swapping around the battery or the wires, so if we swap them around, we then get negative numbers, and so we plot it again and we get one straight line through the origin. Now, when we have a graph like this, we describe it as directly proportional. Graph. Now, what two features make it directly proportional? Well, one is it goes through the origin. So here it is, going through the origin. The other thing that makes it directly proportional is it's a straight line graph. Okay, so that's a typical question, you know, for 2 points. What is a directly proportional graph? Through the origin and a straight line. Pause it, make sure you get all this written down. Now, if we took out this resistor here, say it was, I don't know, a 20 ohm resistor, and I take it out, boop, 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 and get rid of it, and I put in another resistor, I'll go purple, and this resistor had twice the resistance, 40 ohms. What would it do to our graph? Well, if we think about it, voltage is the energy the electrons have. It gives them their push. Current is how fast they can get through. Well, if we make it harder to get through, then the current is going to be lower. So what we end up with this graph is through the origin again, but this time lower. Here we have a big resistance. If we had a small resistance, then it would be up here. And here we can label it small resistance. I'll just put res. Okay, remember you can pause at any point, replay it if you need to. So with that in mind, now let's look at a new component. We're going to take this one out. I'm going to get rid of that. And we're going to put something more familiar. I'll go with orange because they make light. And I'll put a cross through it, and we've got ourselves a light bulb. So I wonder what the graph will look like for that. So we draw it again. I'll go to a clean page. We go insert and pick my graph. We're going to draw it with plus and minus again. So this is graph number 2. You just sketch these. You haven't got to use graph paper. The shape is the most important bit. We have plus voltage plus current, and we have minus current and minus voltage. Well, this time something different happens. I'm going to use orange because that was the colour I drew it in. What we find is the graph goes up steeply and then cuts across like so. And if we turned the page upside down, we draw it again, we get a mirror image like so. Now, what's going on? Oh, I'm going to split it up into some parts. I'm going to take this section here. I'm going to call it region A. And then I'm going to take this section here. I'm going to call it region B. Now, look at the steepness of the graph. Steep. What does that mean about the resistance? Is that a big resistance or a small resistance? So, look back at your previous graph. Steep gradient equals small resistance. So next to it we can write in small resistance. Okay, what about B? The gradient is very small, so we look over to B. The gradient is very small, means we have a big resistance. So here we have a component whose resistance is changing. B for big, big resistance. So we can now write, I'll use orange for light bulb, we can now write the resistance increases with voltage. Now, the question is why? Why would the resistance of this go up when on the wire it didn't? Well, if we looked inside an atom, we would see, not inside an atom, inside a piece of metal, we'd see some atoms. And we've talked about this just before we broke up. Here we've got some atoms in a lattice, a regular shape, and dotted inside are the electrons. So I'll get some electrons like so. Now the electrons want to get through the wire, so they travel along, but they bounce, bang, 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 bang. And as they're going along, they're hitting the atoms. And you can think of the atoms like bells. You know, you tap a bell, it vibrates a little bit. Hit it more, vibrates more. And these atoms are ringing. They're vibrating as faster and faster each time. Now when atoms vibrate, we call that heat. They have heat energy. So the wire is getting hot inside the light bulb, and the light's starting to be given off, and so the electrical energy is being lost as light energy, and off comes light. So it glows, which is what you want a light bulb to do, but the other problem is it also gives off heat energy. And so as we increase the amount of voltage, we're giving more energy to the atoms. The atoms are vibrating more and getting hot. So here it's cold, and here it's very hot. Now I'm going to write that up as a sentence or two to copy. So, as more voltage passes across the bulb, the atoms vibrate more. They turn electrical energy into light and heat. The vibrations make it harder for the current to flow, meaning near the end, meaning more resistance. And that's the region B. Okay, keywords there are definitely atoms vibrating because of the voltage, the electrical energy being changed into light and heat, the vibrations of the atoms making it harder for the current to flow, and that means, and there's the answer to it, more resistance. And that's why light bulbs light up, but they also then have massive resistance. Hopefully you're still with me. Remember, you can pause at any point, have a break, come back to it. Last one, shouldn't take too long, this one. This is a component you see in lesson 1. I'm going to go back to my test circuit. I'm going to take out my light bulb. I'm going to choose a new colour to code it in. I'll choose brown. And I'm going to plug this in. And hopefully some of you will remember this. This is a diode. D-I-O-D-E. And if you remember, it is a turnstile for electrons. It only lets them go one way through. So in this case, the arrow is pointing this way. The electricity can flow this way round. But should it try and get this way, it's going to hit the wall, so it can't get through. So if we now go back to our graph, let's have a look at what that would look like as an IV graph. So we'll go back to our stickers, pick our graph, make it a bit bigger. Let's have a look. So we'll label it up. Plus current plus voltage minus current minus voltage. Okay, remember this plus plus means I can go one way round, tick. But this way round, let's have a look what happens. Okay, so when we plot this, what we find is nothing happens for quite a while. You're given a push, a bit like pushing against a gate. You can't get it to budge, it's a bit stuck. And then all of a sudden you push hard enough where, oh hey, you get a low resistance. So you get loads of current through because the device has just given up. It's not pushing anymore and you could just get through. But what if we now swap the wires around? We change the polarity. This time, it does not matter how hard you push against the wall, you cannot get through. So you end up with a graph that goes along the axes like so. And here we can label up no current can flow. And we'll label that there. And here we've got low resistance. So that's it. Hopefully you're still with me. At a bare minimum, you need to be able to memorize the graphs. So test yourself with something really simple like so. Just tick, tick, like that. In the back of your book, bulb, fixed resistor, diode. Can you draw them from memory? Bulb across and across. Fixed resistor. Oh, less resistance. Oh, more resistance. Yep. And diode. Nope, 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 nope. Yes. Okay, and if you could do this, I'm really happy. And look forward to seeing you all soon. Take care. Bye-bye.